Really happy to present my work titled A Scottish Provenance for the Altar Stone of Stonehenge. Now, why is an Australian PhD student working on rocks that are so iconically British? Well, I grew up in South Wales myself, where some of the famous bluestones of Stonehenge are from. And so I was always fascinated by the site. And I went on to study geology at St Andrews. And here I am. I moved down under to do my PhD. And I had the chance to work on some very small fragments collected from the altar stone. And using the tools and equipment that we have here in Perth, in part due to the extensive mining industry we have here, we can answer some of these exciting questions regarding Stonehenge. And this work was a collaboration with my university, Curtin University, Adelaide University, Aberystwyth University in Wales, and the University College London in England. Just trying to move on. Here we go. So here's a layout of Stonehenge. I'm sure all of you have been there, and today we can visit the site from the footpath and you can peer into the site. You can't actually see the altar stone when you visit. It's partially buried underneath a collapsed trilithon, which is the great upright sarcens that make up the inner great trilithon horseshoe. In the center of Stonehenge is a semicircle of bluestones. Now, bluestone is an informal term for any rocks considered exotic to the Salisbury Plain area, and they include a wide range of different lithologies from rhyolites, dolerites, famous spotted dolerites, but importantly, it includes a sandstone lithology. That sandstone forms the altar stone at the heart of Stonehenge. The altar stone is a 6-ton, flat-lying, recumbent rock that forms a so-called altar at the heart of Stonehenge. Surrounding Stonehenge is the famous Sarsen Circle, which consists of 6 to 8 meter upright silicified sandstone Sarsen stones, and they are from the local area on the Salisbury Plain. Stonehenge now is partially ruinous, and the collapsed Sarsens are spotted throughout the monument there in southern England. And there we go, there's the Salisbury Plain. So as it stands, the Salisbury Plain is a large chalk outcrop in southern England. Some of the rocks of Stonehenge are from Wales, and some, like I mentioned, are from the local area atop the Salisbury Plain. And here's what it might have looked like when it was first constructed. So we have this very architecturally complicated lintel arrangement with the sarsen standing upright, forming an enclosed area, a circle. Inside, we have a circle of bluestones, which then enclose the famous Great Trilithon horseshoe here. Inside this horseshoe is another ring of bluestones, and at the center, possibly, there stands the altar stone. We don't know whether the altar stone has always been flat-lying or whether it stood upright when it first arrived at the site. And of course, Stonehenge has the famous astronomical alignment. In a few months' time, during the midwinter solstice, at least in the northern hemisphere, the dying sun will cast its final rays on the altar stone as it sets, casting light through the Great Trilithon onto the altar stone there. And the opposite happens in the midsummer solstice. Thousands gather there to witness the rising sun rise on top of the plain and shine its light through the sarsen lintels and onto the altar stone. So clearly, the altar stone was a focal point of festivities at Stonehenge today and perhaps in the past. So who built Stonehenge? Well, there are some theories. Some say it was the wizard Merlin himself using his magic to conjure up the sarsens on top of their lintel plinths. Other people think it might have been Irish giants. Maybe Merlin and the Irish giants worked in cahoots to construct Stonehenge. And of course, some people believe they may have had some extraterrestrial help. Well, I think the truth is actually a lot more exciting than those three hypotheses. It was our Neolithic ancestors in all of their ingenuity. Stonehenge was actually constructed over several different time periods. It was added to, it was changed, it was rearranged, but they initially started life as a small earth embankment, a henge. This evolved in complexity with wood structures being erected. This coincided with the advent of grooved ware and beaker style of potteries up in Orkney and also in southern Britain. And at this time, around 2500 BC, the altar stone may have been delivered and placed within the Stonehenge circle. But we don't know when the altar stone arrived, in all honesty. The earliest image of Stonehenge is from around 600 years ago, and it's from an antiquarian drawing. And even that shows the altar stone at the center of Stonehenge, flat lying. So as I mentioned, what makes Stonehenge really unique is the diversity of rocks that make up the monument. So here we have Stonehenge on the Salisbury Plain, and the local sarsen stones can still be found at their source, 25 kilometers to the north, a couple of miles north near Marlborough, in the Marlborough Woods area, the Marlborough Downs area. And they occur as these large boulders within wooded landscapes that probably were collected and erected on the site. The bluestones, the famous and enigmatic bluestones, which my colleagues have worked so tirelessly for the past 20 years to provenance, where they're from in southwest Wales. We've actually linked some of these lithologies to Neolithic quarrying sites throughout the Mynydd Preseli Mountains area in southwest Wales. We don't know how they got to Stonehenge. Some people think it may have been a marine option where, using rafts, they were rafted up the Bristol Channel, along the Avon, and then eventually a short overland journey to the site. Other archaeologists, they envision an overland route taking several months or years, and it would have been a great source of celebration en route to its location in southern England. In any case, even today, traveling from southwest Wales to England can be a long and arduous journey, so it must have been very difficult. Some people think glaciers may have moved these rocks from the Mynydd Preseli area to Stonehenge, and that is also a theory worth considering going forward. So here we have a summary of the building blocks of Stonehenge. We have these famous sarsen stones, large rocks at Stonehenge. They're from the westwards, local to the area. We have the igneous bluestones from the Mynydd Preseli area in Wales, around 250 or so kilometers away. That really has left the altar stone. We don't know where it's from. For a long time, it was thought to have come from Wales, along with the igneous bluestones, but recent work has begun to move away from that. And here we have its last known when it was last exposed during an archaeological dig back in 1956. And here we can see it partially buried below the collapsed Great Trilithon. And from here was where one of the fragments that I analysed of the altar stone was collected from a small broken bit of debris here. And today, when you visit Stonehenge, yes, you really can't see the altar stone. It's a very unphotogenic rock at Stonehenge. And here is my colleague pointing at the altar stone there, exposed in its central location. So let's take a closer look at the mineralogy, any kind of clues contained within the rock that might help us work out where it's from. Well, in all honesty, it's a rather drab-looking green-grey micaceous sandstone. It does have a distinctive mineralogy. There is a appreciable amount of barite in the altar stone and no kind of case bar, a certain kind of feldspar. There are no fossils to speak of in the altar stone. And this has led workers to previously associate it with the Old Red Sandstone, which is a really famous package of rocks that crop out throughout Britain, Ireland, the North Atlantic area, including Norway, Svalbard, even as far as the United States. But for me, luckily, as a geochronologist, it contains numerous uranium-bearing minerals, such as the famous zircon, rutile, apatite, mica, the list goes on. And here we have automated mineralogy maps of the altar stone. So an instrument will scan the thin slice of rock and produce a map of where the minerals are located within the rock. So you can see here you can see the layering in the altar stone very faintly here, but it really is just dominated by quartz, calcite, plagioclase. In other words, a rather ordinary sandstone. And as I mentioned, minerals can be atomic timekeepers. We know that uranium decays to lead. Uranium is a large, atom is unstable over geological time, and in a process known as radioactive decay, it will turn to lead. We know the rate at which this change occurs. It's known from laboratory studies, from fieldwork. It is a rate of change that is not affected by temperature or pressure. It's a fixed constant. So using that, we can do something quite powerful indeed. We can tell the time as geologists. Right, I want you to imagine a magma ocean, a volcanic chamber under the earth. In that, there will be some uranium and there will be some lead floating about, waiting to be incorporated into a crystal. Here we have a crystal of zircon crystallizing from that magma. When zircon crystallizes, it only incorporates uranium into its crystal lattice. It is really happy to do that. Things cool, the magma crystallizes, the rock freezes, in other words, and some time will go on. Some of the uranium has decayed to lead at a rate that we know. We know the rate at which uranium will turn to lead. Let's give it a few more 100 million years or so. And you'll notice that this ancient grain now has a lot more lead than it did when it first formed. In other words, we can measure the ratio of lead to uranium to work out when the crystal formed, or in other words, the age of the rock. So I should say, not all geochronometers are built equally. What if this crystal here incorporates some lead at the time of crystallization? That would really complicate things. This so-called common lead is a nightmare. It's really difficult to account for, but it must be corrected for to give you a good and reliable age. And that really has formed the basis of my PhD, because we rely on the mineral zircon, but there are hundreds of other uranium-bearing phases, such as apatite. So we can imagine zircon as this fantastic Swiss Rolex of a Swiss watch of a geochronometer. It only incorporates uranium, it's durable, it's robust, brilliant, perfect. Maybe apatite, which incorporates some lead during crystallization, is a bit more of a cuckoo clock. It is fun, and it can tell you other things about the rock and the history of magma crystallization, but you have to account for that so-called common lead. So let's turn back to the altar stone here. And I just want to highlight kind of the scale at which I've been working at. I wish I could go up to the altar stone and hammer a bit of the rock off. Unfortunately, I think English heritage would frown upon that. So I'm left with these small fragments of historical fragments from the altar stone. And I have to work at a really high spatial scale to squeeze as much information from these precious fragments as I can. So we shoot a laser at these crystals to ablate, to vaporize a small fragment of the crystal, which we can then analyze the composition of the gas that's released. We analyze the composition of that gas for that uranium to lead ratio I was telling you about. So we're working at the scale of less than a human hair. The laser that we shoot at these rocks is less than the diameter of a human hair. At this scale, we could be shooting bacteria with the laser. We can see that. That's the scale at which we're working on. And look at this beautiful zircon from the altar stone here. We can see the laser ablation pit I left in the crystal, but these beautiful concentric, almost like tree rings of growth within the zircon. They are telling you a story in and of itself. And the apatite here, not quite so beautiful, but for me, a lot more interesting in the things it can tell you. So here we have a mount of these grains from a different kind of rock, and we can just shoot all of these grains to build up an age fingerprint. So that grain might be 100 million years old. This grain might be 500 million years old. That might be 3 billion years old. And building up this age fingerprint is an immensely powerful tool. Now, with that immensely powerful tool in mind, how do we figure out where the altar stone is from? Well, in some ways, this is just a classic geological problem. You have a rock with an unknown provenance. You can imagine maybe a glacial erratic on a beach, or a fossil in a museum collection that didn't have any good records with it. So we have a rock with an unknown provenance. Or in my case, we have a rock in a field in England at the center of a monument where we don't know where it's from. This rock is a sandstone. The altar stone is a sandstone, which means it's made up of lots of different grains, each with a unique age and chemical characteristic that we can measure. We know the characteristics of rocks from the crystalline basement and other sedimentary rocks throughout Britain and Ireland. So you can see where this is heading. We can make a comparison between the altar stone and a potential source in Britain. And detrital studies like mine have been used in the archaeological sciences before. We've figured out where pottery is from. We've figured out where axe heads are from. We've figured out where other masonry is from. So it really was just waiting to be done on the altar stone, in my opinion. So let's see what the rocks of the UK are like and what kind of comparisons we can make. So for such a small area, the geology of the UK, as you all well know, probably is very complicated. From south to north, it is different ages of rocks. It's different characters of rocks, sedimentary to igneous to metamorphic. In the south, southern England, Wales, and England are composed of a crystalline basement called East Avalonia and Magumia. Going northwards, we have Ganderia, which also forms part of southern Ireland. Going even further northwards, across the Iapta Suture in the southern uplands, we have Laurentia. Now, these terrains also extend as far across to Canada and mainland Europe, because once upon a time, these landmasses were together. They were proximal to each other, and with the opening of the Atlantic, of course, these terrains, these rocks have been dispersed. The Old Red Sandstone is a rock package that sits atop all of this crystalline basement, and it's a late Silurian to Devonian sedimentary rock package. It's quite old, in other words. It really does deserve its name. Now, the Old Red Sandstone will reflect the underlying basement. Sedimentary rocks, you can think of grains of sand on the beach. They form from the erosion of mountains, of igneous rocks. They are a reflection of the rocks that surround them. You can think of the igneous rocks being their parents and the sedimentary rock being a child, and they will have some of the DNA, the detrital grains of their parent rocks. So let's take a closer look here. We have lots of igneous rocks that form the Grampian terrain in northeast Scotland, and they are a reflection of very old magmatism, at least in the British context, of around 400 to 500 million years old. And these igneous plutons, like I said, are well constrained to their related event, Caledonian, Variscan orogenies, mountain building events. So we know that the Old Red Sandstone is a reflection of the nearby geology. We know that the altar stone probably is an Old Red Sandstone. Let's see what the zircon can tell us. So across three fragments of the altar stone, I managed to get 56 reliable, robust ages. I was really strict in how I made sure that there was no common lead, that the ages were undisturbed by any later kind of process like metamorphism, carefully imaged each grain I shot. So with these 56 ages in hand, what are they telling us about the altar stone? Well, our ages spanned 498 to nearly 3 billion years old, well over half the age of the Earth. So if you ask me how old the altar stone is, I say it depends really. It can be, you could consider it as young as 498 million years old or nearly 3 billion years old. It truly is an ancient has an ancient history. Of course, it has an ancient archaeological history, but to me as a geologist, it has this history of a 3 billion year old grain within it. Kind of remarkable stuff. But importantly, these grains come together to form age peaks at around 1 billion years old, 1.6 billion years old, and 1.7. These age peaks, these age populations of zircon, they correspond to known events. We know what was going on at this time within the rocks that surround Britain and Ireland and North America. We can relate them to mountain building events. Let's have a look at the age signatures of the basement terrains of Britain. So this is a statistical plot here, but in other words, I took the ages that form these basement terrains I mentioned in Britain and Ireland, and you can map them almost like the closer they are together, the more similar they are, which makes sense, right? East Avalonia, the basement of southern England, is quite similar to the basement that forms, southern Ireland, north of England, Gandaria. The basement of Scotland, Laurentia, you'll see how far it is from East Avalonia. It's very different. It's far from each other in Euclidean space here. And these age populations of zircon are what make it different. Laurentia, the basement terrain, is dominated by old geology here, 1.6 billion years old, nearly 3 billion years old geology here, which pushes it away from other terrains. Okay, so knowing that, let's have a look at what sandstones are telling us in this statistical plot. Okay, so we have old red sandstones with data that was published for zircon that I could take from the literature, replot. Okay, so what have we got? We have the Anglo-Welsh Basin and the Dingle Peninsula Basin being very similar. The Anglo-Welsh Basin is a really large package of ORS that crops out along the border of Wales and England. It forms the famous Brecon Beacon Mountains. But it's interesting how similar it is to Old Red Sandstone in Southern Ireland. These basins really are a reflection of their underlying geology, and the geology of Wales and Southern Ireland is similar. The Midland Valley Basin here is kind of unique, really, in its own way. It is defined by a age population of around 1200 MA, so it's unique and very diagnosable. The famous Orcadian Basin, of course, in northeast Scotland, that crops out in Caithness, in Orkney, as far north as Shetland, is very distinct from other terrains and other old red sandstones. In fact, it's most similar to old red sandstone that crops out on the Svalbard archipelago, which is strange to me how far away that is. But back then, at the time of formation, Svalbard and the Orcadian Basin were right next to each other. Svalbard has been kicked off through fault movements. Okay, so our 56 altar stone ages, how do they fit into this? Well, let's plot them on this plot. It's amazing. When I first did this nearly 2 years ago and I saw this such distinct Scottish signature, I really couldn't believe it. So I immediately had to recalculate all my ages, and time again, I got this Scottish signature from the altar stone. If we use statistics, we can say that it's actually statistically indistinguishable from the Orcadian Basin. So detrital zircon within the Orcadian Basin and the altar stone, they're, for want of a better word, the same. And they're very similar, or at least close together, to Laurentia too. So amazing stuff, really. And there's a better way, or maybe a more kind of clear way of showing this. Let's have a look at cumulative probability plots. Okay, so along the bottom here, we have ages of zircon from these old red sandstones and from the terrains here. I've just highlighted the important ones to pay your attention to. You'll notice that the shape or the detrital load, the cargo of these classifications is very similar. They conform to each other. They're the same shape going up this plot here. Brilliant. These are the other terrains of Britain, so East Avalonia, Magumia, Gandaria, that I explained. So let's have a look. What do these plots mean? Well, we can see that Laurentia and the Orcadian Basin are dominated by this 1 to 2 billion year old detrital zircon cargo. These other terrains, they mainly contain young 500 million year old zircon. How does the altar stone fit into this? Well, let's have a look at its distribution of zircon ages. It conforms to the detrital zircon load of the Orcadian Basin so neatly. It's really kind of beautiful to see that. And like I said, they are statistically indistinguishable from each other in terms of their detrital zircon load. But there are other minerals from the altar stone that we can date. And what do they tell us about its history? Well, let's have a look. But before I do that, I'm just going to show you a basin level plot. So here is only Old Red Sandstone showed. And again, look how closely the Orcadian Basin in brown here and the Altar Stone conform to each other. This Svalbard Old Red Sandstone I told you about too, it's a bit different, but again, it's the shape of these lines that's important. And we can see here, it has the same shape, especially in terms of its, Proterozoic zircon load here. The other terrains are very different, and the Midland Valley is kind of a unique sedimentary rock package, as I just explained. Okay, so other minerals. Now, apatite is so different. It responds very differently to uranium-lead analyses than zircon. Concordia plots are a really simple graphical way of showing ages. Here, the ratio of uranium to lead increases, which makes sense, right? Younger rocks towards this end of the plot will have more uranium. They've had less time to decay to lead. And the same here, older rocks will have more lead compared to another kind of lead. But what's important to know here is that within the Altar Stone, there were two groups, there were two ages of apatite. An age that we didn't see in zircon analyses of around 462 plus or minus 4 million years. Now, for anyone that knows the Grampian terrain, that kind of age will be ringing some alarm bells. That was the age of Caledonian magmatism, Grampian magmatism in that terrain. The second age of around 1 billion years old is a reflection of that basement rock I was telling you about. That is a Laurentian age. We can relate that to this Grenvillian, which was a kind of orogeny, a mountain building event that happened in Laurentia and Laurentia only. What makes apatite especially interesting for me compared to zircon is that apatite is a rather weak mineral. It's actually what makes our teeth and our bones. And with enough acid, it will dissolve and it won't survive persistent transport. You might remember that 3 billion year old zircon I showed you. Zircon's great because it will survive and persist through geological time, but apatite, it really won't. It will break down and be destroyed. In other words, if you find apatite in a rock, it's telling you about rocks, it's telling you about source rocks that were nearby. So if we're seeing a apatite with an age of 462 million years old in the Altar Stone, that means that there must have been igneous rocks of that age nearby. Bear that in mind. So with these ages from the Altar Stone that I showed you, I then went to the Orcadian Basin and I analysed samples from Caithness, and look how similar these apatite loads are in both rocks. The apatite from the Orcadian Basin gives us again that mid-Ordovician age of 466 plus or minus 6 million years old. And again, we see that hint of an older Laurentian component coming out of the basement rocks of northeast Scotland, of the Grampian terrain. And from a sample of Old Red Sandstone from Orkney, again, we see with a bit more uncertainty this mid-Ordovician igneous component. So apatite, tick. Zircon, tick. They are both pointing towards an Orcadian Basin provenance. Now, we're lucky in Australia to have very novel and new techniques being developed. And I was fortunate enough to go over to Adelaide, the University of Adelaide, to use another kind of isotope system, lutetium and hafnium. And much like uranium and lead, they can give you an age for a rock. And they can give you really good ages for apatite too. They're especially good for apatite, which incorporates both of those isotopes during crystallization. We see a few other age components, but most importantly, again, we see in the hafnium isotopes from the Altar Stone this mid-Ordovician Paleozoic age component, early Paleozoic age component. And again, we see a complex history of Laurentian Proterozoic magmatism. So with that in hand, we can look at the chemistry of apatite. See, this is why I love apatite. It's so powerful, not just for an age, but for its chemistry. It really is a very powerful mineral. So the trace element kind of profile, or what the trace element, the chemistry of apatite was telling us, was that it was telling us a very diverse story. it was telling us that these detrital apatite was sampling a very compositionally diverse source area during the mid-Ordovician 460 or so million years ago. And for me, that is just a reflection of the lithological diversity of the Grampian terrain. We have granite plutons, we have gabbro plutons, we have everything nearly in between those two end members that crop out in the Grampian terrain. So these apatite are just a reflection of the diversity of their parent rocks that I mentioned earlier. And finally, just for due diligence, I turned to another uranium-bearing geochronometer, rutile. Rutile is common in metamorphic rocks. It's common in some kind of igneous rocks, especially granitoids. And what do we see again? Well, much like apatite, we see this mid-Ordovician Paleozoic age component. 451 plus or minus 8 million years ago was when this rutile crystallized. And we also see it points towards the Laurentian component there with group 2 rutile. So 3 minerals are telling us basically the same story, which I think is pretty amazing, how they're all kind of converging on the same answer throughout all of our analyses. And here we have it, the only place really for me in Britain and Ireland that could account for this age signature that we see. As I mentioned, we have these famous, the granites that form the Cairngorm Mountains here. But of course, we have gabbros, the Inch gabbro, we have the Aberdeen granite. We have so much lithological rock diversity in the Grampian terrain that it is reflecting the diversity that we see in our apatite chemistry, our zircon ages. We have this Laurentian basement, this ancient, very old basement rocks that are intruded by a compositionally diverse suite of igneous rocks that at 450 so million years ago, this terrain began to erode, and all of the detritus being shed from these mountains at the time was shed northwards towards the Orcadian Basin. So this is what it looked like 450 or so million years ago. The Grampian terrain was a mountain range. It was the Caledonian Mountains, the famous Caledonian Mountains. And the Orcadian Basin was just trapped in between these mountains as a intermontane kind of valley basin that was getting this rapidly eroding mountains, and all of the detrital uranium-bearing minerals that I would one day date in Australia were being fed into this lake nearly 500 million years ago. It's kind of amazing to think about. Britain, southern Britain, Wales, and England were about to collide, or were in the process of colliding, with Scotland and North America and Canada. And for us, importantly, the igneous rocks that were erupting here were of a very different age and chemical signature than the ones that were occurring in Laurentia and Baltica, this distinctly older package of rocks. So let's turn back the clock and have a look at northeast Scotland some 450 million years ago. Orkney, northeast Scotland, Caithness, was part of Lake Orcady, this amazing and beautiful inter-mountain valley that was composed of, we had lake sediments, we had delta sediments, and amazingly too, we have some of these beautiful fossils, early fish fossils that are preserved in some of the rocks that I analysed from Caithness. So it's remarkable that these mountains in Scotland were eroding, supplying grains to a lake that would then be squished and turned into a rock. That rock would then be brought up to the surface, where for some reason, Neolithic Britons decided to take that very same rock on a journey southwards, some 700 kilometers. It was just the perfect stone they wanted for their altar in their monument. It's a crazy geological and archaeological dimension to think about. Now, I'm not an archaeologist myself, but there is something that connects these seemingly random assemblage of images here, and I'll talk you through each one. So let's start with this cute fella here. He is the Orkney vole. The Orkney vole, he's new to the island. He was introduced to Orkney around 5,000 years ago. He was probably a stowaway on a boat, carrying hay or cattle or rock to Orkney from mainland Europe. So he's an interesting facet in this story. And of course, Orkney and Northeast Scotland, it has some amazing Neolithic monuments. The Rings of Brodgar, the Maes Ho. These are just amazing Neolithic monuments that are constructed of Old Red Sandstone from the local area. But for many archaeologists, Northeast Scotland and Salisbury Plain, these were the kind of population centers during that time. So was there connectivity between these two groups? Well, if we look at isotopes and also bone remains from Stonehenge and from the surrounding area, it looks like Neolithic Britons were moving. They were a very mobile people. We find evidence of people having grown up in not the Salisbury Plain, but coming to Stonehenge for ceremony, for ritual, or indeed for feasting. This boat here is a bit younger than Stonehenge. It's around 2000 BC, from around 2000 BC. But trapped within this boat, remarkably, were the preserved remains of rock that Neolithic Britons were shipping. Of course, on a much smaller scale than the 6-ton altar stone, but they were a people interested in moving masonry around their island. And this image here, we have to imagine what ancient Britain must have looked like. In other words, it was a temperate, it was a cold rainforest. And I just couldn't imagine moving a 6-ton rock across this formidable landscape. Yeah, today traveling from Scotland can be a long and hard journey. So with a 6-ton boulder in hand, it must have been a very difficult feat indeed. And so for me and for our team, that pointed towards marine shipping as a really feasible and worthwhile option to consider as to how Neolithic Britons brought the altar stone to Stonehenge. Some might say glaciers did it, and that is an option that I would love to investigate at Stonehenge and the surrounding area. And it may well have been on a multi-glacial journey. One glacier moved it south, one moved it west and east. It might have been done over time. With enough time and enough ice, anything is possible. And with that, I'd like to turn to the kind of the final implications of our work. So like I said, we favor anthropogenic human transport for the altar stone. And for us, this has some implications for the connectivity in Neolithic Britain that I'm really excited for my archaeological colleagues to think about and really kind of get into the details about how connected these two groups were. But for a geologist, this multi-mineral approach to detrital grain studies is such a powerful tool. And I think the altar stone really was just a beginning. Any rock or gemstone or masonry, axe head, pottery, we can work out where it's from. And that has some amazing implications for me of we could really constrain ancient trade and culture throughout not just Britain and Ireland, but Europe and indeed Australia, where I'm working right now. And with that, I will say thank you, and thank you for listening, and I'm happy to take any questions. Thank you.
Thank you very much, Anthony. That was a fantastic talk. It was a great story and well told, and just an amazing piece of work. You had some really impressive results there. So if anybody has any questions, do pop them in the chat. I'm just thinking about this with my museum hat on. Where is the altar stone kept? Like the fragment that you worked on, is that kept in a university or?
It's the two fragments that I was lucky to work on were kept at the Salisbury Museum, and they have since been returned to the museum. But there are numerous fragments of the altar stone that I understand are kind of kicking around, and they have all kind of been authenticated to the stone based on non-destructive means of looking at the altar stone, and they've been linked to the stone. But there's lots of altar stone fragments around.
Yeah, cool. Okay. And for your laser ablation, did you have to make a thin section, or what was the kind of prep work?
So these fragments of the altar stone were in thin section form.
Okay.
Luckily,
okay.
That's something that stood the test of time. Geologists did it back in the 1920s, antiquarians did it in the 1840s, and they are still as useful today as they were then, but for a very different reason.
Yeah. Oh, fab. Lots of people in the chat saying thank you so much for the talk. I had a question about where the recording will end up. It'll go on the Scottish Geology Trust YouTube channel. So I can find a link to that in a sec. Somebody asked to see the penultimate slide again, but I think you're already there.
Yep, sorry, here we go. Yeah, this is these are the ages of the basement terrains that I compiled, and also some other Old Red Sandstone, just for your reference here.
And a request for the one after, the slide after.
Oh, here we go. Yeah, this is a reconstruction of glacial flow. I didn't get a chance to talk on this, sorry. But one of the reasons why we, my team, kind of didn't favor glacial flow is that a lot of reconstructions will show the northwards movement of ice emanating from the Grampian and the Cairngorm Mountains, taking material even further away from southern Britain, northwards. But I understand that perhaps a multi-glacial route might have pushed it out to the North Sea or pushed it towards the Irish glacial stream, and it could have indeed ended up in Salisbury Plain. And I'm really looking forward to working and hearing from glaciologists about this possible mechanism.
So we had a question from Rich Arthur. Interested in the fault that is supposed to have been sinistral, making the north coast of Scotland stick up further, and this is based on two granites once being joined. I noticed these seem to be missing from the map.
Ooh,
So
the map of the geology map of this one here?
Possibly.
Yes, that map. Indeed.
Can you clarify further? What
Could you please repeat the question?
Yeah, sure. Can you hear me?
Yep.
Yeah, I can hear you.
Okay, thanks. Where it says Great Glen Fault, somewhere around about Inverness and probably quite a bit further south of Great Glen, on the two sides of that fault are two granites, Strontian and Foyers.
Mm-hmm.
And the story goes that they were once joined, which means that the fault that you've got your dot on, that side of the fault, was originally much further up and has been dragged downwards, so that the shape of the Orcadian Basin is a nice sort of V shape, whereas originally it was much further up to the north. If that fault was the other way round, if it was a detrital fault, then the line of the coastline you see there in the Moray Firth would line up with the what's the place called, John O'Groats, the whole coast of Scotland would then be just one straight long parallel line, which kind of sort of seems intuitively right. But I can't see either of those faults, either of those granites on either side of that. Well, it wouldn't be on one side because the map's blank on one side, but
yeah,
it is interesting. I mean, that's still very much up in the air, isn't it?
Yeah, no, agreed. And
which way it went.
For some, the Great Glen Fault extends all the way, indeed, to Svalbard, right? So it really is this.
Sure.
It's this crustal scale fault.
Yeah.
I didn't get time to mention, but some of the chemistry of the apatite points towards a source from the Northern Highland terrain too, from the Glen Dessery syenite pluton. That's a very distinct pluton with a very distinct chemistry. So it could have come from there too. The Northern Highlands was a minor source of detritus, but yeah, the Grampian terrain was the main one.
Yeah. Have you spoken to Brian John, by the way? He's a great glaciologist who's very keen on a glacial origin of Salisbury Plain. There's quite a lot of evidence. There's quite a lot of glacial stuff in the rocks around the Salisbury area. It's quite interesting. I've just written a paper about the Anthropocene, and my fellow geologists have just chucked it out. It's interesting. I think we can fairly safely chuck out the Anthropocene, because you just mentioned anthropogenic transport, and clearly that didn't happen in the 1950s. My personal favourite is that we should mark our we have these dates you're talking about. We've got a really good date spike. It's called the occurrence of plastic.
Yeah,
because prior to sort of 1950, prior to the sort of atomic elements that we produced, they weren't there. So I tend to favour BP and PP before Plasticine, and post-Pleistocene. So I think we should call it the Plasticocene, not the Anthropocene.
I'm inclined to agree. And on a similar note to that, I think in the is it Scarpa Flow in Orkney, is they use metal from boats that were sculled there because they haven't been contaminated by radiation from nuclear testing. So NASA uses them in very high-tech sensitive instrumentation because they haven't been contaminated by our activity since the 50s.
Sure. But I mean, it's such a clear marker, a single point in time, that to try and say, oh well, it doesn't happen. I guess it's a bit like what we're doing with archaeology. We talk about BC, you know, and presumably we're going to have to start sometime talking about the future. You know, the Holocene isn't going to last for another, you know, millions and millions of years. We're going to have to start thinking about saying, okay, let's you know, why don't we start geological time at 0? And yesterday was 4.5 billion years and 1, and tomorrow will be 4.5 billion years and 3. It makes it a bit messy, but you get my point.
I do, yeah, I do. And on the glacial aspect, yeah, there's so much yet to learn, I think, and I'm really hoping to do some work now to resolve and help, you know, answer this glacial question. And I'm really looking forward to working with glaciologists and other geologists to use these dating tools to hopefully, you know, unravel some of these questions.
I don't want to hog this, but I've just been in Brittany, and there's a load of glacial stuff there. So you know, so it's interesting. Yeah.
No, yeah. Again, like I said, enough time and enough ice, anything's possible.
Yeah.
Thanks, Rich. Just to bring it back to the final few questions, because it's getting a bit late for you in Australia.
Oh yeah, sorry.
So we've got a question about is it possible to look at the quantity of detrital minerals from the altar stone to kind of compare it to whereabouts in Orkney you might have sourced the stone from?
Yeah, so in this study, I looked at apatite, zircon, and rutile. Each one will respond a bit differently to transport and other later rock processes like metamorphism. So I'd love to look at mica, muscovite, or biotite mica. I'd love to look at clays, calcite. Anything that will incorporate uranium will tell you a story. And I think the more information that we can get from the Orcadian Basin and the altar stone to make these comparisons, the better any provenance interpretation will be. So, like I said, I think this work really is just the beginning.
So somebody's asked about sketches or photographs of the altar stone before it got buried. You did have a photograph of the altar stone in your talk, but I think it was still covered, right, at that point?
Yes. So the earliest drawing of Stonehenge we have, I think, is from the 14th or 13th century, around then, and it shows the altar stone partially buried. So from that time onwards, it's always been buried, but you know what it was doing from that point before, we have no idea. But it was probably, I believe it was always probably flat lying.
Okay. And somebody suggested that maybe you could do a similar study from stones actually on Orkney, e.g. the Ring of Brodgar, if you're allowed to chip a bit off. And I think that might be the stumbling block right there.
Yeah, no, I would love to. There's a lot of Old Red Sandstone in Orkney, so really the hunt is on now to find where it's from in this rather large basin.
And we've got a couple more comments saying, thank you very much for a wonderful talk.
Thank you.
So if anybody has any final questions or comments? And if not, I think thank you very much for speaking to us tonight.